Array elements A0, A1, AN minus 1 are sorted into a binary search tree. The tree will then be used to search for a given element. The average case, big O, for inserting all elements and searching for one element respectively will be what? So we have to first look at what is the average case shape of a BST. So for a BST, the average case means that it's gonna have a random input, and that means that the BST is roughly balanced. And we know that the height is going to be equal to approximately log n. Now after this, this is our first step. We have to look at the average case, and then our second step is that we have to insert n elements. So if we insert n elements, we know that each insertion is gonna follow one path from our root to our leaf. And we know that path length is approximately gonna be our height. So then we can write that as O log n. So then we do this n times. So that's just multiplying that by n. So that's going to be O n log n. So now after this, if we search for one element, which is the last part of our question, we know that search, it also follows one path down the tree, down. And since that's just one time, that's just going to be O log n times 1, which is just O log n because it's multiplying by 1. So that's why that's the answer. Now, move on to our next question. Return the sum of the leaves 0 for empty. Sum of the leaves in the tree, 0 for an empty tree. So, well, what this means is that, like, we have to first detect the leaf. After that, we have to return the value, and otherwise, you have to sum the left plus the right. So, what is a leaf? This means a leaf means that you have to double check if it's null, and also that the right is equal to the null. Or sorry, I meant to say that the left. Both of them have to be null. So we had to find the replacement for the code here. So here we have that if tree is equal to null, it's going to return 0. Else, our second case is that it has to be, the left side has to be null, and also the right side has to be null. So which one do we see here? Well, we see that here. We see that in E, we have that if the tree on the left is equal to null, and also that the tree on the right is equal to null, then you're going to return the integer of the tree get value of the integer. And then here, elsewise, you have tree return the leaf, the sum of the leaf, tree of the left plus leaf sum, tree get right. So what this means is this is right because it only returns value if it is truly a leaf, unlike the other versions, truly a leaf. Also, our internal nodes contribute nothing. You also recursively add leaf values. Other ones are wrong because here you have to use this and not that. So this had it, but like that's not, this one didn't have it. And okay, my bad. Wait, this one had it, this one did not have it, and this one had it. And also here, let's see what else. You also don't add +1, that's wrong. So a blank binary tree contains the maximum number of nodes for its height. So it's gonna be full because for a full binary tree, this means that every level is completely filled, and we know that max nodes for height h, that's going to be 2h plus 1 minus 1, and no other binary tree can have more nodes for that height. Now, next question. In a full binary tree with n levels, there are blank nodes in each level n. The answer is 2n, because let's look at a level pattern, and like if you have a tree like this, you have 0 or just like nodes like this. Let's make a couple levels, and let's make it full. So in this case, we can see that we have 2 to the power of 0, that's equal to 1 node, 2 to the power of 1, that's equal to 2 nodes maximum, 2 to the power of 2 is equal to 4 nodes max, and then 2 to the power of 4 is equal to, it's equal to 8 maximum, or sorry, that's 2 to the 3. So that means the nodes at the level maximum is going to be, oh, this is, well, it literally says full binary tree, so it's always going to be that. So it tells you how many nodes there are. Now, next question. Public int what's it? So the method what's it returns -1 for an empty tree. What does method what's it do when invoked for a non-empty tree? So if it's not empty, if the tree is equal to null, it's going to return -1. That's important. So what happens for a leaf node? So non-empty tree. So our case 1 is when you have a tree that is empty. And then our case 2, we're going to say this is when you have a leaf node. So for a leaf node, this means that tree is not equal to null. That means that the left child has to be equal to null because it's the leaf. And that also means that the right child has to equal to null. So that means that what's it is gonna null, and that's gonna equal to -1. Then that means that you're gonna have x is equal to 1 plus -1 is equal to 0. And then you're gonna have y is equal to 1 plus -1 equal to 0. Therefore, your leaf height is equal to 0. So this method, it computes at each node, you're gonna have 1 plus max height left height right and this is the definition of this whole thing is the definition of height of your tree. That's because your height is equal to the longest route to leaf path. It's not gonna be 1 plus height because we already have that. Since empty is gonna equal to -1, empty is equal to -1, that means that the leaf will return 0. So this already returns the correct height. Next question. Do we have this page? Wait. Do we have a question 19? We do. If two binary trees contain exactly the same items, the two trees are always exactly the same. So if you have tree 1, let's do like two binary trees. So let's say you have like this example where you have like 1, 2, 3. If you have 1, 2, 3, then it's gonna look like this: 1, 2, 3, because on the left it has to be smaller, on the right it has to be larger. Now let's say that you have 2, 1, 3. That's gonna be 2, 1, 3. And if these are gonna be the same items, but they have different shapes depending on what order they were listed as. So our answer is going to be false. The search of a binary search tree potentially can throw away 1/2 of the search space after each comparison. Well, when you have a balanced BST, at each of your comparisons, if your target is less than your root, that means you discard your right subtree. Now, if your target is greater than your root, then you discard your left subtree. And that's gonna eliminate half of your remaining nodes. Just like a binary search. So that's why your answer is true. Now we have one more question. It's over here. So, which of the following statements correctly inserts the object as the right child of the node that points to something? This. So, here, that's going to be p.set right new tree node object. The reason is because tree new node, this creates a new node. And then set right, what this does is it attaches it as a right child of P. The other ones are wrong is because this one, P equal to tree node object, P get left, P dot right, this is going to replace P entirely. No attach P as right child. This is not a constructor. This incorrectly assigns P's children to the new node. And this one is gonna reassign variable, but it does not attach to the tree. Consider the following method: public int x sum tree node root. If root is not a root, we're going to check if root is equal to null, and if it's true, then you're going to return 0. Now return integer root dot get value. So get the value of integer of the root of the integer, or yeah, the integer of the root. Then x sum root dot get left. plus x sum root dot get right. So what our formula is that at every node you're gonna have value minus left sub tree plus right sub tree, and this is not normal addition. What this does do is it subtracts the left subtree. After this, you're gonna work bottom up. So what this means is that so that's first that we have. Second, we work bottom up. So what this means is that you start at the leaves, and so you look at node 12. This has I'm just gonna point to it. No children. So you have 12 minus 0 plus 0 is equal to 12. Now let's look at node 3. On your left side, you're gonna have null. And then on your right side, you have 12. That's your other leaf. So then you're gonna have 3 minus 0 plus 12 is equal to 15. 3 minus 0 plus 12 is equal to 15. Now for node 4, you're gonna have on the left on the right, you're gonna have null. And then now for node 7, you're gonna say this is just your leaf, so you don't have to do anything. It's just gonna be 7. And then for node 1, you're just gonna say leaf. Well, that's not a leaf because it has one child. So that's null. And then for 2, you're gonna have your left is 7. And then for 2, your right is gonna equal to 1. So now for 5, your left is gonna equal to negative 11, and then your running out of space. Your right is gonna equal to negative 4. So I'm gonna write this like here. Your formula. So now negative 11, 4. So then you have here for root 2. Oh, we can also write this for root 2. Wait, we also have to write the expression for 3 or for 4 as well. So 4 is going to be 4 minus 15 plus 0 is equal to negative. That doesn't look good. 4 minus 15 plus 0 is equal to negative 11. So now for 2, you have 2 minus 7 plus 1 is equal to negative 4. Now for 5, you have 5 minus negative 11 plus negative 4. That's equal to 12. So your entire tree, like if you calculate it, it's just going to be 12. Wait, 2, negative 7, positive 1, 2, 7, 1, 12 plus 0, 12, right, 12, 7, 2, 7, 1. Actually, for node 1, you're going to consider this to be the leaf. Now for our second question, a binary tree of height d can accommodate a maximum blank number of nodes. So how do we get this? We know that our height is equal to d, and you have your max nodes when tree is full. So your formula is gonna be 2d plus 1 minus 1. That's because, again, as we've seen, like for a binary tree, like you just think of like a complete tree, but just like it just has the possibility of like not being filled. But like, for example, like it could be like this, but it still has the max. Like a binary, like a complete tree is still binary, but a binary tree is not always complete. So you have like at level 1, it's like you have 1 to level 4, and you have 8. So your total is equal to 1 plus 2 plus 4 plus dot 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 plus 2d, and that's equal to 2d plus 1 minus 1. Now next question. Consider the following method. Public ints magic tree node root. If the root is not equal to null, then root.getLeft. You check if the left is equal to null and also if the right is equal to null. So if magic root.getLeft plus magic root.getRight. So then you go back and you have to check if that's equal to 0. So you're gonna have a temporary variable, and that's gonna equal to the left value, and then you're gonna set the left equal to the right. So whatever your value at the right of your root, and then you're gonna take your root and you're gonna set it equal to that, and then you have your right, and then you have your temp. So when does magic equal to 0? So when does this method have a what does this method do to a tree that's referred by roots? So whenever it takes in roots, it's gonna return 0 for leaves. Now that's our first step. Now we want to find our condition. So our condition is if both children return 0, that means that you have your magic of left plus your magic of right, and that's gonna check if it's that 0. So that means that your left child is leaf, and also that means that your right child is leaf. Therefore parent has 2 leaf children. So what this does, like, let's think about the functionality of this. What happens here? So first, it sets the temporary variable equal to the left, right? So temp is equal to left. After this, we have left is equal to right. Oops. So then you have left equals to right. And then after this, you're going to set right equal to the temp. So here's left. Let's write this out. So you have right and your temp. So you're going to say temp equals to right. So then you're going to say left is equal to right. And then you're going to say right is equal to temp. So what this does is it swaps 2 leaves. And what swapping is, this is the definition of in order. So next, or sorry, that's not it. I don't know why I said that. So what visits the left, the root, and traverses the right subtree? Wait, this just swaps it. So, but you could use a traversal method to implement that, or no. Okay, so which binary tree traversal traverses the left subtree, visits the root node, and then traverses the right subtree? So that's the definition of in order. You just have to memorize that. In a BST, if a node is removed, if a node to be removed has a left child and a right child, the removed child's value is replaced with the, so binary search tree, you're going to take the largest value in the subtree. You have 2 children. What you have is that you replace with either the largest in the left subtree or the smallest in the right subtree. But you look at left first. Look at the second. Next, a blank is a tree in which each node in the tree is greater than or equal to the left, equal to its left child, less than or equal to its right child. So this is going to be a BST. So these ones are going to be all greater, where each node is greater than or equal to its left child. So you have a child here. This is going to be less. So here you have your child on this side, your node is here, and then your child is here. So your child has to be greater than your parent, and your parent has to be less than your child. Your parent has to be less than your child. And that's for, okay, so your node of your parent has to be less than your right child. So which binary tree traverses the root node, traverses left subtree, and then traverses the right subtree? So that's preorder. So here you can remember that is pre. You can just remember pre, like before children, in, between. You just remember that it's in between left and right. And then post is just after. Given that tree node root points to a non-empty BST containing comparable objects, the methods below try to return the maximum value in the BST. Which methods actually work? So what we first can do is we can look at our options. We can trace like each of these. So first we have to know that in the BST, your max val is equal to your rightmost node. So here, what this means is that you keep going right until there's no more right child. So first you check if the root on your right is equal to null or not, and then you have your root and you're gonna have that equal to the right, and then you're gonna return that. So you keep going right until there's no more child. So see, this is like right here, and that finds the largest val, because in a BST you're gonna have small here and large there, and that's your like parent, and then everything is like diverging from here. So for object max tree node root, this is gonna be recursive. So what we can see here is like you have if root get ring is not equal to null, so that's like your condition. So it's gonna keep saying object temp is equal to max root dot get right. If comparable temp dot compared to max value is greater than 0, your max value is equal to temp. So it goes recursively right until it can't and it finds your rightmost val. Public object measure root. So object max value is equal to root.getValue if root.getValue is not equal to null, and also that comparable max root.getLeft compared to max is greater than 0. So you have max value equal to max root.getLeft, and then you have a second if statement if root.getRight is not equal to null, and also comparable max root value is greater than compared to max greater than 0. Max value is going to equal to the max of the root right. Interesting. So what this is going to do is it checks both sides recursively. Okay, but it means that eventually can find the maximum. Yeah. So your first one's iterative, your second is recursive, and the third one recurs over the whole tree. Less efficient, but consider the following method. Public boolean sum property tree node T. Return T if it's not equal to null, and also if the left is not equal to null, and also if the right is not equal to null. And condition sum property T dot left, sum property T dot right. So the condition is that, so you have that either the node has both children here, or the left has such node. Or the right subtree has such node. So this returns true if there exists at least one node with two children. One node with two children. In a full binary tree with n levels. So this question asks, what is true for a binary tree with n levels? And are there two n plus 1 minus 1 nodes? So here we have a full binary tree, and that's when each of the nodes, they have two children. So here it's fully filled out. This node has two children, this node has two children, this node has two children, and each of these are levels. Level 0, level 1, level 2, level 3. So here there's one node, here there's two nodes, here there's 4 nodes, and here there are 8 nodes. So 2n plus 1 minus 1 is equal to the total nodes if n is equal to the height of the tree, and the root is equal to height of 0. So what we can see with this is that, like, if you have at n equals 3, you have 2 to the 3 minus 1 is equal to 7. So the levels are equal to 1 plus 2 plus 4 is equal to 7. So there is a caveat to this, though. You might get confused when you have this question. When you have 2 times leaves minus 1, this is when n is equal to the total number of leaves rather than the total number of levels. So when you have a full perfect tree, that means that your node count would be 2 to the power of n minus 1 instead. Next question. Each integer on a list of random integers is inserted into a binary search tree. Next, the tree is traversed and the integers are reprinted. Which traversal would duplicate the order of the original list of integers? So for this question, you need to know what the insertion order is and how it relates to the traversal order. So remember that insertion order does not equal to traversal order. traversal order. Let's analyze what each of these are. In order means you have this sorted order. In order traversal, preorder, I meant to put this here. In order means you have a sorted order. Preorder means you have a root, first, structure, order. Preorder traversal means that you have the leaves first. Level order means you go by level. But none of these, none of them guarantee that you have the original insertion order. None guarantee original insertion order. Unless the tree is extremely special, but usually this will never happen, is extremely special. That would be a really rare case special. Usually no. So that's why we're going to say none of the above. Given that the tree node root point to the root of the following binary tree, consider the following traversal: public void traverse tree node root. If the root is not null, not empty, traverse root dot get left, traverse root dot get right, system.out print the value of the root. Then you're traversing the root dot get right, and then you traverse dot left. So what you're gonna have is, we're gonna expand this for A. So let's do this for A first. For A, first you're gonna have traverse B here, which is on the left. And then after that, you're gonna have traverse right. So then you're gonna traverse C, which is on the right. Then you're gonna do system.out print root.get value. So that means you're gonna print A. After that, you're gonna go to the right, so you're traversing C again, traverse C. Then after that, you go to the left, so then you traverse B. Now let's do this for node B. First, you're gonna look at the left. At the left, there's gonna be nothing there, and on the right, there's also nothing there. So when you have B, you're gonna say left is null, your right is null. Then you print out the value of that root. So then you print B. After that, you go right. So when you go right, you have to see that right is going to be null. And then you go left again, and then you see that your left is null. So then this is going to be the same thing for C. So we see C here is going to be the same thing. Let's copy and paste this. And I'll make this a different color. That's going to be C. So C, the left is also null, and your right is also null, so you're going to print C. So when all of this prints out, you're going to have B, C, A, C, B, because these are null. And that is corresponding to answer D, which is 5 letters, and also that exact order. Now for question 13, what is the height of a full binary tree containing n nodes? So when you have a full binary tree, your total nodes is gonna equal to 2h plus 1 minus 1. So now we want to solve for height h. So when you do that, you're gonna have that n is equal to 2h plus 1 minus 1. So plus 1 both sides. You're gonna have n plus 1 is equal to 2h plus 1. Now you're gonna take the log base of both sides. So you're gonna have log base 2, and then you're gonna have log base 2. Okay, yeah. And then after that, it cancels out that 2. So you're going to have log base 2n plus 1 is equal to h plus 1. Now you're just going to subtract 1 from both sides, and then you just have h is equal to log base 2n plus 1 minus 1. So that is answer C. To implement the level order traversal, it is convenient to schedule node visits using a queue. Well, first, how did we figure this out? So first you had to ask what level order. So level order means that you're going to have a breadth first search, which is going to be a BFS. And when you have a BFS, it visits nodes by the level. So you're going to have level 0, level 1, and level 2. So now, what data structure supports FIFO? So first in, first out. You want this data structure. And if you remember, a stack is LIFO and a queue is FIFO. That's because the first node is added. First node added is also the first node process. So you can think of this like when you're standing in a queue as a bunch of customers, the first one who's standing in line is the first person who's going to be served, or is the first person to check out at a grocery store. So let's go into our next question. Suppose traverse is defined as follows: public void traverse tree node root q generic type e q. If the root is not equal to null, then you're going to traverse the left and q, and then traverse the right q dot add root dot get value. So what we can see here is we have traverse left, traverse right, and q dot add root. So this is going to be a post order traversal, but instead of printing, it stores in a queue. So for our tree, it's going to refer to this. So what we're going to do is we have post order. Post order means that you have left that goes right, and then that goes to the root. So the order added to the queue, order added to queue is going to be D, E, B, F, F, G, C, A. So then at the front of your queue is going to be D. So then when you get to here, your next part, q string q is equal to new linked list, traverse root q, system.outprint q.remove. What it's going to do is it's going to remove your first element. And the first element in our FIFO structure is going to be D. So that's why D is removed. Now for our next question, we have suppose traverse is defined as follow: public void traverse tree node root stack E. If the root is not equal to null, you're going to push S, and then root dot get value, traverse root dot get left S, traverse root dot get right S. So we have S push, and this is going to be of the root, traverse, this is going to be of the left, traverse of the right. So what we can see about this is going to be a pre-order traversal pushed onto your stack. So then this pre-order is going to be for this tree. We have A, B, C, and then A, B diverges D and E, and C diverges F to D. So our pre-order traversal is going to be A, B, D, E, C, F, G. So you go A, B, D, E, and then you go C, F, G. what is printed when the following statements are executed? Stack string s new stack traverse root s system.outprint ln s.pop. So what you have is this is going to be a stack, and then your top is at the right of this. So we can write A, B, D, E, C, F, G. G, this is G. So we have pop. So when you have pop, we know that a stack is going to be our data structure. So when you have a stack, it removes the last that is pushed. And the last thing that was pushed was G, which is, we can see here. So our answer is going to be G. In what order does post-order traversal algorithm traverse a binary tree? So when you have a post-order, it's always going to be left, right, to the root. So we can see here left subtree, right subtree, then root node. So that's why C is our answer.